All right, hello everybody. This is Dave Moore. I'm a solutions architect at Elastic, and I want to go through today a webinar on something that I think is of interest to many people, especially people who are going to go production with our software, Elasticsearch. This will be about how you could size Elasticsearch like a solutions architect and make smart decisions on how to go big when you're ready to do that. So prefacing all of this, I want to give a sense of why people would choose Elastic when they go into production. And from there, I want to map kind of the things that we do that are interesting with the ways in which you actually get there, which will be the point of this webinar today. A lot of people use Elasticsearch because under the hood, they can trust that it will give them the insights that they need with lots of data that comes in very fast over time, and to get those pieces of information instantaneously. So for example, a lot of people here who travel are familiar with Uber, which is an application that can pair you with highly rated drivers if you yourself are highly rated and the ones that are closest to you. Those types of questions that have to be answered in real time are powered by Elasticsearch in a very big deployment. On Yelp, we are also powering search. So everything that you do for finding highly rated cuisines that you prefer within some geographic region and finding certain areas that are open for you, all these types of questions also powered by Elasticsearch. Many different ways that you interrogate data are the ways that Elasticsearch can give you a foundation for doing all sorts of different types of search and data analytics. And when you're operating at scale, that's where we have to think about how do we make smart decisions on how to power that experience. For those who are unfamiliar, we do offer a full stack of software to help make all of this possible. And at the heart of everything that we do is Elasticsearch, which is the distributed scalable search engine. And so whether you are on our download it, do it yourself version of Elasticsearch, or if you host it in our Elasticsearch service or Elastic Cloud Enterprise, all these different models of deployments are using Elasticsearch under the hood. And that's what we want to focus on today, is to zero in on that middle layer here of Elasticsearch. How do we go ahead and make a decision on what we need in terms of resources and what configurations to power one of these great use cases? So the point of this webinar today is I want to help you master the art of capacity planning for Elasticsearch. Whether you're using Elastic for logs, metrics, traces, or search, or whether you run it yourself or in the cloud, to have a healthy and performant cluster, you have to make smart decisions going forward in terms of how much resources, what kind of resources. Elasticsearch itself can scale. So if you find that you've undersized or oversized yourself, you can scale to what you need. But you got to start strong so that you have a successful operation. And so the goals of this webinar is to think systematically. These are the best practices, frameworks, methodologies that solutions architects at Elasticsearch use to figure out what might be the right configuration starting off for your deployment. Okay, so to think about that, I think about this in terms of a stack, where at the very foundation are computing resources, where the data actually resides, how the data is read, how it's computed. And from there, we can think about the architecture of Elasticsearch, its components, and how it uses these different resources. When we understand these two things, then we can start to think about what are the methodologies that we would use to actually conduct a sizing. What would be the questions that we have to ask? And what are the things that maybe we have to measure? And how do we ultimately come to a recommendation on how big things should be and how they should be configured in a way that's viable? So I'll start with a preface on computing resources, which many people here might be familiar with. I want to make sure that we're all oriented on the same page, and we're going to refer back to when we start talking about the mechanics of Elasticsearch, how it actually comes back to computing resources. So the four basic computing resources, at least the types of things that we consider when we're sizing Elasticsearch, are storage, memory, compute, and network. And if I had to analogize this, I would say that I think about it in terms of a book and how you think about and interact with a book. In storage, you have the words that are in a book. The words are stored in the book. You might have a very big book, and you might read that book, and you might start by reading maybe a paragraph at a time, or a whole chapter at a time, or maybe just go word by word. Those words that you buffer inside of your head, that's your memory. So the more that you can fit into memory, the more that you can process that data very quickly, imagining what you've just read, analyzing it, and that's your compute. And then finally, maybe you take what you've learned and you speak about this with other people, and that would be the network. So if any one of these is undersized, you create a potential bottleneck. think about memory, for example. Think if I was reading a book and I had to read and think about every single word at a time, then there's a lot less of an ability for me to really understand. But if I could somehow read that entire book in my memory, and in any given second, I know absolutely every word that's inside of it, that's amazing. And it would be like a savant, and I could think about so many different things about what I just read very quickly. So all these different capacities, we want to make sure that they are appropriately sized. Not any one of these is under-resourced. When it comes to storage, storage is probably the most important resource that we think about as solutions architects when we're sizing Elasticsearch. And there are some best practices that are here and there, both in our documentation and in our training courses and in the blogs, and trying to cull all this information together to give you a sense of what are some of the best practices, absent of really any benchmarking. What would we recommend? For storage, we see really great performance with solid state drives locally attached. Other types of SANs as well can be beneficial and give you good performance when you're doing reads and writes, which are some of the fundamental operations that you have to do in Elasticsearch. So we recommend these types of storage media and attachment methodologies for hot workloads, let's say, things that you're very frequently searching. And Elasticsearch also gives you this ability to tier up your data and say, let's have a longer tail of data. Maybe we're logging data over time and we store 7 days worth of data that's recent that we really care about. We put that in our really hot, expensive hardware. Maybe we'll store a whole year's worth of data in a more economic fashion, maybe using hard disk drives, spinning disks, and using a different way maybe of attaching that, like block storage. And we might call this the warm tier or the frozen tier. And if we really need to start scaling out, we could also think about doing things like RAID 0, which can help improve our performance as well. I would say the only thing we really recommend against is using something like a network attached storage where other applications might be sharing resources on that network and interfering with the operation of Elasticsearch, in addition to just the overhead at the protocol layer that NAS incurs. Going into memory, we think about memory in 2 different ways. On the one hand, when you start up Elasticsearch, there's this concept of heap, which is what I would say is like the business objects that Elasticsearch works with. The cluster metadata, the index metadata, shard level metadata, and segments, all this type of information is stored in the heap. There's also some data that we store in there as well for search and analytics, but for the most part, we will leverage the operating system cache, the file system cache, and I'll explain that in a second. For the JVM heap, there's a recommendation that we have in general for the data nodes to have about 50% of your RAM on the host be allocated for the JVM heap, but no more than 30 gigabytes of RAM to avoid certain issues with garbage collection. The rest of the available memory on the host will still be usable and beneficial for Elasticsearch. So typically we recommend that people have a node that is, let's say, 64 gigabytes of RAM, but sometimes you might want to bump that up to 128 gigabytes of RAM, which gives you more available memory to store the data in a cached format that is allowing you not to search by hitting the disk every time. That's more of your data that is being held in memory. And even if you've got a data set that isn't going to fit entirely in memory, think about Zipf's law for a second, which is this idea that if I'm an e-commerce website, for example, I know that 80% of the people at some point are going to search for iPhones. And so there's going to be a small segment of data that is very frequently searched by so many people. That's going to be stored in the operating system cache, which is great. There will then be a longer tail of less popular data that might be hitting when people search it, and that's acceptable as well. So if you really want to speed up the performance of Elasticsearch, adding more memory to each node, even if it's not on the heap, is a good thing that you can do. As far as competing resources, I think that this comes into play when we think about having lots of traffic, either index-heavy traffic or especially search-heavy traffic. 2 things that you might think about would be the thread pools and the thread queues, which are available on each node. These are like the workers. So if I have an 8 CPU core computer, each with 2 threads, I've got 16 workers available to do work. If they're all tied up, they have to start queuing up the work. And if those queues get filled, then the operations that you request can actually just get dropped. So this will be something that we think about in the future. How do we plan for that? And then finally, network and the bandwidth associated with network. In general, I have found that network bandwidth is not usually a resource that you have to plan for unless you're going at really large scale, probably like petabyte scale. That is potentially a point of failure where the actual links that are connecting your nodes or egressing from the cluster to the outside world, that can become saturated. In that case, you might think about ways that you can deal with that. In fact, our cross-cluster search feature, which was predated by the tribe node before that, first came about because we had to solve this problem. And we decided that we would create cross-cluster search as one way to help isolate some of the traffic coming between all these different nodes and having them work in concert. Okay, so this is the basics of computing resources. Now that we have a sense of understanding on that, we can move into the Elasticsearch architecture and how are these components of Elasticsearch using those computing resources. Start off with some terminology so we're all on the same page. I'll say the word cluster, and when I say that, a cluster is a group of nodes that are working together to operate Elasticsearch. A node literally is a Java process that runs Elasticsearch. Usually what we find is there's one node on a actual machine, although as we've becoming more of a cloud-first company, we do make use a lot of containerization as a way to maybe have multiple nodes that are more efficiently using resources on the hosts. An index is, and I guess let's say if you come from the database world, you might be familiar with like a database or a table. This would be similar to that. An index is a group of shards that forms a logical data store. So what is a shard? Shard is a Lucene index that stores and processes a portion of an Elasticsearch index. The Lucene is an open source search engine. It was actually made by the same person who made Hadoop, Doug Cutting. And it's effectively what we do as Elasticsearch, what the software does is orchestrate many individual shard or Lucene indices as if they were one larger index. And that's how we can scale. That's the elastic in Elasticsearch's ability to coordinate all these different data structures together. Lucene itself has one more significant, let's say, way of breaking up data, and that's called a segment. A segment is this immutable piece of data where that's where the data actually resides. And when you write or search data, you are writing and reading from segments. It's not something that we often have to actually think about from a sizing perspective, but there will be some cases when I talk about how Elasticsearch works where it's good to have awareness of that. And then finally, there's a document, which is the record that you put into or out of an index. And I actually use that word like submitted to and retrieved from very carefully because what you store in Elasticsearch isn't necessarily going to look like what you put in. So the document is what you see, but ultimately that document is going to get split up and stored in many different ways in different data structures. And that does have an implication on sizing, and we'll get more into the details there. Many of you might be familiar on the left-hand side here with our architecture diagram of our basic pieces of software that form the Elastic Stack. We're going to zoom in here on the Elasticsearch segment on that. And we bring that up. And inside Elasticsearch, you have a cluster of these nodes, right? And these different nodes can play different roles, like the coordinator node and the ingest node and the data node. And these nodes can play multiple roles, or they can all play individual roles. For the most part, when we do sizing, we think about the data node. And on the right-hand side here, you can see what might we see if we were to look deeper into what is happening inside of a data node. There is literally a file system, a directory within it, and that is where we store the indices, which are the Lucene shards, which ultimately have the data. There are other things that we could potentially think about when we do sizing. For example, if we have a machine learning heavy use case, we might want to think about how to size for machine learning nodes. We won't address that in this webinar today, but it's something to be aware about. As far as what these different types of nodes do, we've got a little example here that helps summarize that. Again, data nodes are primarily the things that we think about for any use case because you have to have the data somewhere, and any index or search that you do is going to be on a data node. And these are probably going to be the most resource-intensive nodes that you have. Obviously, they're going to be extreme on storage usage, but they can also potentially, if you're doing things like aggregations and ingest nodes, which might be compute intensive, they can also do a lot of compute and memory intensive workloads as well. Ingest machine learning nodes are more specialty type nodes, and they can be also heavy both on compute and memory. The other types of nodes that will probably be relevant for you for anything that you do would be the master nodes, which manage the cluster state. They don't actually do too much in terms of resource consumption. So my recommendation for people is you can have 3 dedicated small master nodes that aren't co-located with any other type of node. And if you do that, you're likely to be in a good situation. These, again, they don't have to be too big. Maybe 8 gigabytes of RAM could be plenty. But as long as it's not on a data node or a machine learning node, that's probably the key thing that you want to do, is to keep them dedicated. And then lastly, you've got this concept of a coordinating node, which is simply a node that will take an API request and make sure that it gets done. It's itself not going to probably do that. If there's like a search request, it's going to forward the search request to a data node. If it's an index request, it's going to forward that to a data node, and so on. So every node is a coordinating node, and you can't disable that functionality, but you can have nodes that just play the coordinator role. And there can be a time where it makes sense to do that. And I'll get to an example of that in a bit. Okay. That is the high-level architecture of Elasticsearch and the nodes. And for the sizing perspective, I think it helps to understand the basic operations of data that you would work with, which are writing data, reading data, updating data, deleting data, your essential CRUD operations. In Elasticsearch, you could think of those as being, a write would be an index. You have a document and you put it into the index. You can delete the document or you can update the document, and eventually you want to be able to search that document. All these different data operations have their own requirements in terms of what types of resources they use. So if you understand at a basic level how a single index operation works, or how a basic search operation works, then at scale, when many of these operations are happening, you can think about, okay, this will probably be a compute-intensive workload or a I/O-intensive workload. So let's look at these a little bit more closely. When you're indexing data, I've kind of drawn out the data processing flow here. You have an application, we'll call it the client, that wants to store a record inside of Elasticsearch. What it's going to do is put that record, as we call it, to some coordinating node that's ultimately going to be ensuring that this happens. If the client has requested that we process the data first with ingest node, for example, FileBeat will invoke the ingest node in many cases to, let's say, geolocate an IP address. So if we do that, it will first route the request to an ingest node to provide that geolocation data and enrich the incoming document. Then this document's going to then be routed to a data node where the data is going to reside. And potentially, if we've said that we want to replicate this data, which in most cases we will for high availability and data loss prevention, that data node will also be responsible for sending a copy of the record to every other data node that's going to hold a replica of that document. So each of these data nodes is now going to be putting the document into a shard. And what happens there is we take this JSON document and we have to parse that, meaning we have to look at all the different fields and we have to determine, is this text, is this a date field, is this an integer? And all these different types of data are going to go into potentially different data structures. Text-based data is going to go into an inverted text index. And text in particular is something where we could expect some more compute-intensive work, because when we process text, when Elasticsearch processes text, it's going to split apart that big text field into individual tokens, which are basically words. So if you've got a Wikipedia article, for example, that's many different words, and that's lots of different ways that we have to think about in terms of splitting the text into words, getting rid of words that we don't care about, like the or and or because, and so on. And then finally, maybe normalizing those tokens and putting that into the index and counting the frequency of these different tokens. Fairly compute intensive. And if you have really complex, what we call text analyzers that are responsible for doing this, that can slow down your indexing throughput. All of these requests are buffered up and they're finally committed and written to disk after, by default, every 5 seconds or so in a new immutable segment that is inside of Lucene. A lot goes on when we're doing the index request. This is a way to kind of summarize that. And at the bottom here, you can see how I've kind of sectioned where all the different resources are being consumed at different points of these requests. If we were to delete a document, it would be similar in the sense that the client would submit a delete request to the coordinator, and the coordinator will route that to wherever the data is. And those data nodes will be addressed again. And it'll say, we want to mark this document as deleted. Now, that's interesting because when we mark a document as deleted, we're not actually deleting the document yet. Rather, the document's marked as deleted, and anytime we do a search, that document is just going to be skipped. So there's some redundant data that is still being consumed on disk. And there's a background operation that happens every now and then, which you can also manually invoke. It's called a segment merge. What happens is that these segments are ultimately optimized and reduced. And this is the point at which all of the documents that you marked as deleted will finally be expunged and no longer consuming resources on disk. There's something to think about from a sizing perspective. If you delete a lot of documents, then you might actually not be, for a period of time, freeing up space. And it's something to think about. Similarly, when we update a document, remember that documents are immutable in Elasticsearch. So when we update a document, we're actually marking the old version as deleted and then inserting a whole new document with whatever updated fields that we have. So this has the cost both of a delete and an index operation, although we don't invoke any ingest pipelines. So there will sometimes be a use case where you have to update data a lot. And I think the best way to think about that would be, let's say you have a terabyte of data, and then every day you update 10% of that. From a sizing perspective, I would say treat those updates as if you were just indexing more documents. Because the worst case scenario would be you do all that 10% of your updates before the segment merge happens, and you could actually be storing 1.1 terabytes of data. And then finally, we get to search, which for us is a generic term that just means information retrieval. And there's different ways that Elasticsearch can execute a search. Some of them can be very simple, like getting a document by an ID. Some of them can be more intensive, like an aggregation, which is how Kibana, our user interface, will create charts. A typical type of search will be one where we do like a relevance-based search for, let's say, a Wikipedia article or a Yelp restaurant. So this search process typically goes in a fashion that we could informally describe as scatter, search, gather, and merge. And that looks something like this. You have our client. We say we want to get some data. We send that request to a coordinator. The coordinator is going to scatter this request to the data nodes where this data might be. By default, we don't necessarily know where the data is, so we just know where the indexes are and where the shards are. So if I have an index that I'm searching, it has 5 shards, I have to hit all those 5 shards to be able to see if my data is there. Potentially, you can speed this up and make it more efficient by including what's called a routing parameter, which you also have to use at index time. What this means is that when you index a data, you could force all data of a certain category, let's say, to always go in a certain node. And then if you also specify that when you search it, you're only going to hit that one shard. If you've got 5 shards, you're only going to be searching that one shard. That can help free up a lot of compute resources so you could allow for more search traffic. An example might be if I am a news website and I'm categorizing messages by maybe some topic, let's say Trump or hurricanes or elections, all of the articles that relate to this topic will all go into the same shard. And then when someone searches that, we know that we're always going to pull from that shard. So routing can be an important way. If you want to think about how to improve performance of search, look into that. Once the request finally gets to the data nodes, each shard that's participating in the search has to do the same logic that goes into indexing a document. It has to parse it. It has to split up the text the same way that it was split up when we indexed it. And then the shard is going to search all the different segments that it has for the data. When all the hits are found, those are going to get sent back to the data node, back to the coordinator, and the coordinator, before it sends the results back to the client, has to merge those results. Because we just did what is potentially a distributed search, if we want to provide a single list that is nice and neat for the client, or especially if we're doing something like a count or an aggregation like that, we have to finally merge all this together. And that is where the coordinator can actually play a role in the search process. This is called the merge. And it's important to think about if you have a search-intensive use case, but also, let's say, an index-intensive use case, so you're just indexing a lot and reading a lot, it might make sense to have a dedicated coordinating node to offload that merge process from the data nodes, which also have to be indexing a lot of data. So those are the individual types of operations that deal with data. Now, if all of these operations, if you were to do them over and over and over again, indefinitely, you could think of that as being a use case. I might have an index-heavy use case where I'm predominantly doing indexing requests. And that might be a logging, metrics, security, APM type of use case. I'll search the data, but not nearly as frequently as I'm indexing data to it. By contrast, I might have a search-heavy use case where maybe my data set is more or less static. It might grow relative to the indexing-heavy use case insignificantly. And maybe I update some data here and there, but for the most part, I have an application and I'm searching it, and I'm providing search experience for hundreds of thousands of people. Or maybe I'm powering a website that's doing the same. Or I might have like a BI application that's primarily just analyzing data and not really writing to it as much. I could be doing an update-heavy use case, which I don't see as much, but there are people who, for example, will use Elasticsearch as a cache or as a system of record, where the data set's fairly static. It's also searched now and then, but data is also frequently just updated. And remember that when we do that, it's as if, from a sizing perspective, that we were inserting data temporarily. And then you'll finally have use cases that are just going to use all of the above. And I can think of some examples with financial services institutions that we've worked with where they might have a record that is very big. They call it a transaction, and it probably represents a very big multi-stage transaction, like you go and buy a house and there's many stages involved with buying that house, many different actors and statuses and things happening that all get logged in a single record. Those are then provided to consumers as information. So there's a lot of people searching the status of these transactions, but there's also just a lot of transactions happening. So there's just a lot of activity happening, indexing, searching, and updating. And when you're sizing for that, you have to think about just making sure that you have enough resources to power all of those different types of use cases. Okay, and then before we get into the sizing methodologies, I think it makes sense to think about how data is actually indexed, because many of the use cases that we work with deal with index-heavy use cases. But even if it's not an index-heavy use case, you do still have to store the data. And to plan for how much storage you need, you really have to understand, when I put in 10 bytes of data, how many bytes am I actually storing in Elasticsearch? So what happens to data when I put it in? The first thing that's going to happen is this thing called JSON conversion, where I might have had a CSV file that very densely represents my data. And the way that it's going to be stored in Elasticsearch is going to be in an expanded format. Then the data is going to be split up and put into different indices, and I will have a chance to compress my data, and then finally my data is going to be replicated. We'll zero in on each of these for a little bit. So I have a document over here on the right-hand side. I might have a document that was in a log file that was pure data. Everything that's in it outside of maybe the spaces that separate these values is data. When I store this record as JSON, all the data values are also prefixed with the name of the field. So in your Excel spreadsheet, you know that at the top row, you might have the name of a field. Well, that field is also embedded in every single value of a JSON document. So every row would also have the field name. So what that means is I might have had this record that had 47 bytes of data, but now with all the additional information that I'm putting into it, that same record in JSON could be 89 bytes. So going from CSV to JSON, already I can expect that if I measured 1 megabyte of data on CSV, it might be, who knows, 1.5 megabytes as JSON. This whole JSON object is what we call the source field. And we store that in Elasticsearch as is, because it allows us to rapidly send that information back to the client application without having to pick apart all the values from the indices where the data actually resides. You can actually disable this functionality. In other words, these data values that are highlighted in these colors here are still going to be indexed in a certain data structure that you can search, but you won't be able to pull back. If you disable the source field, you won't be able to pull back the actual JSON object. And so why would you do that? Well, you wouldn't do it if you had a logging use case, because the point of a logging use case is to get back to the source of truth. Who did what when at a certain point in time? But if you have something that doesn't require going back to a single discrete event, then you might not need it. For example, a metrics use case. If I'm monitoring the metrics on my laptop, and the memory usage, CPU usage, and disk usage over time, there's never really going to be an individual nanosecond that I care about. I'm always probably going to be looking at some aggregation, and I'm going to produce a chart that looks at maybe the last 5 minutes or 5 seconds or some span of time of resource utilization. And because I'm doing that, I don't have to get back to the source of truth. So maybe I just don't even sort at all. That could cut down my space by half, potentially. You do sacrifice some functionality, though, if you do that. For example, if you try to re-index your data, but you don't have the source field, then you won't be able to do that because it relies on that field. In general, I would say if you're trying to find ways to cut on your storage usage, you probably don't want to do it by getting rid of the source field. Rather, you can use more aggressive compression. You can look at how you're indexing your data and find maybe other ways of optimizing by, let's say, discarding what you don't need, for example. So speaking of indexing, in addition to storing the JSON, what about the actual data? We take the values and we put them into different data structures. For example, text goes into that inverted text index. Numerics and geodata might go into these BKD trees. We take the values and sometimes we store them in multiple ways. By default, we'll take a text value and we'll store it both as an exact value, which we can use for rapid aggregations, and as full text search, which may or may not be what you want. So you might have had this log record with 4 values, but you actually indexed 6 values by default. Maybe you're never going to use full text search when you're searching for an IP address, and you're only going to be using IP addresses in their exact format. If that's the case, you could get rid of that text field and only keep the keyword field for the IP address, and that will help cut down on space. Elasticsearch does compress all the data by default, and this primarily applies to that source JSON record. And by default, we use this algorithm called LZ4, but you can use a more aggressive and slightly more compute-intensive algorithm called deflate. And in Elasticsearch, we call it best_compression. This can help save additional space as well. And that can get you down to, let's say, 20 to 30% typically is what we see in terms of the amount of storage that you save by doing this. And then lastly, in most cases, you're going to want to replicate your data because you probably are using Elasticsearch because it is elastic and allows you to, as let's say one node goes down, still have your data available somewhere else for searching, both so that you can serve those search requests or also just to make sure that you don't lose the data. So when we replicate data, we're storing a copy of everything that we just talked about in a different shard on some other node. And so thinking about, how do I plan for that? Calculate how much data you expect, and then just multiply it by however many times that you want to replicate it. So to illustrate, if I had a log record, we see at the top here, what am I actually storing? This takes everything that we just talked about into account and illustrates that. I have the log record stored as JSON. I have all the indexed values. And then I have a whole copy of everything that's stored in a replica. And then that data is all compressed. And maybe we can get rid of 25% of everything that we see there. In this case, we see a net expansion of data in that we put in a megabyte of data. Maybe we see 1.75 megabytes actually being consumed on disk or more. It can also go the other way around. Some people, for example, have XML data, and that's more verbose, and they might see some storage savings as they start compressing it down into JSON. All right, so we've looked at a lot of different moving pieces and how they interact with computing resources, and that finally brings us to some sizing methodologies. And I would categorize 2 different sizing methodologies. One that is focused on volume, which is either data volume and making sure you have enough storage, or shard volume and making sure that you're not over-sharding your data. And I'll talk about what that means. The other type of sizing that you may consider is throughput-based sizing, which is making sure that you have enough compute and potentially memory or network resources available to handle the expected number of operations happening at once at some given amount of latency and throughput for each of these operations. I think this mostly applies, for example, to a search use case. Starting off with volume-based sizing, and specifically data volume-based sizing, this will be an exercise that you should do for every cluster or deployment that you expect to run, because you have to store the data and you have to make sure that you have enough storage. And so some of the questions that I would ask customers if we were helping them understand how big their deployment should be, we'd be starting off with how much raw data are you expecting to index per day? And then how many days will you retain that data? Those are probably the two overarching questions, thinking about, especially if you're a logging or metrics-based use case, you're always going to have data coming over time. So have to think about, at some point, we have to cut off, how many days we're actually going to store this data, because we're going to run out of space eventually. So how much data per day and how many days do you want to retain it? Then they'll get into a conversation on how are you actually measuring your ingest rate. So I clarified it up at the top and said raw data in gigabytes per day. We still have to think about, what does that really mean? Is that as you measured it on the file system as a CSV file? Was it in another database that you measured? And if so, was that database compressed? In the raw format, I'd have to factor that decompression in, and that might be bigger than I thought it was. What's going to happen when it turns into JSON, or as it's indexed, or after it's compressed in Elasticsearch? These different adjustments, we have some kind of rules of thumbs for, but it really helps if you can actually take your data and store a sample of it in Elasticsearch using the schema or mapping that you expect to use in production, and just see, here's the expected actual amount of data that we plan to have in the cluster. You take all that, you multiply it by however many times that you're going to replicate the data. And then at some point, we're going to get to a number, which will be the total amount of data, and more broadly, the total amount of storage when we factor in having enough free space in the operating system to do other just operations. All that gives us a sense of how much storage are we going to need across the whole cluster. But then how do I translate that to some number of nodes? And that's one of the key questions. That affects potentially licenses for Elasticsearch, or just how much you're going to spend on infrastructure, how many instances and what type of instances. So to get to that number, we use a RAM to disk ratio to help come to that conclusion. And it's also the methodology that we use in our hosted Elasticsearch service on Elastic Cloud, and our Elastic Cloud enterprise platform that powers the orchestration of Elasticsearch. The way it works really is you have some total amount of storage that you expect, and the memory to data ratio means that if I have a 64 gigabyte node and I want to store logging-based data, I probably want to have 30 gigabytes of storage for every gigabyte of memory that I have. We call that a ratio of 1 to 30. If you have a search use case, that might be a bit tighter. It might be a ratio of 1 to 16. So 16 gigabytes of storage for every gigabyte of RAM. A frozen index might be a ratio of like 1 to 200 or more, potentially, storing much more data on a single node. With the idea being, right, that with more of your data available in memory, the faster your searches will be, which is why having like a 1 to 4 ratio, where you just have comparatively much less data per node and just more nodes with more RAM, that's going to be more data that you can store in the file system cache and get faster searches. So I've got the math up here. So for anyone who wants to kind of do this themselves, you can take these formulas, plug in some of these numbers, and just see what your results come to. Thinking about sharding as well. Sharding is not necessarily like a free resource. Every shard that you have in your cluster incurs some amount of metadata associated with it. So there is an ideal maximum number of shards that you can have on a single node. And one of those magic numbers that we've observed is that you shouldn't exceed more than 20 shards per gigabyte of heap on the node. So for your standard 30 gigabyte heap Elasticsearch node, that would be 600 shards. One thing I would say is that if suddenly you see that your cluster is just performing poorly, one of the first things I would ask people to do is to look and see how many shards do you have per node. Because if you've got our recommended node size, or let's say our conventional node size of 30 gigabyte heap, which would be maybe on a 64 gigabyte RAM node, but let's say you've got 3,000 shards on it, you might start to notice some performance issues. At the same time, one of the ways that you might solve that is having fewer, bigger shards, but there's also an ideal, usual, like maximum size to a shard. So what we've observed again, and this varies, is that if you start to exceed 40 gigabytes per shard, then you might also run into different like slower searches or longer recovery times. So that's another metric that you could think of as being a sweet spot that you want to stay under. If you can balance these two metrics, then you should allow yourself to have a more healthy cluster. And finally, we'll get into search-based sizing. And so when I think about search-based sizing, I'm primarily thinking about it from like a throughput perspective, making sure that we have enough compute capacity in the cluster to service the amount of traffic that we need without the queues filling up and dropping search requests. What I can't do really is predict how fast a search is going to be based on some hardware that you configure. Other than the very basic, more RAM means faster searches, SSD is going to be faster than spinning disk, but I can't really get more granular than that. That's something that really that you have to plan for and observe yourself. My recommendation for people is have a very small but representative sample of what your cluster is going to look like. Have 2 nodes that are the same grade of hardware that you're going to use in production, and then just test your searches there. How fast are they going to be on average in terms of number of milliseconds? There's too many variables that go into trying to estimate that without doing that. So treat that as a constant, your average observed search response time, and then think about what's going to be the peak hour of like the peak season that we have to size for in terms of amount of traffic coming to this cluster. If you can take that peak number of searches per second and your average observed response time for searches, what you can do is estimate how many threads you're going to need across the whole cluster in order to make sure that you're not filling up your search queues faster than they can be consumed. Right when that happens, you run into the risk of dropping search requests. So it's actually a fairly easy calculation to do because each data node has a fixed number of threads in it. And you can estimate the number of threads that you need by factoring in these 2 variables, peak searches per second, average search response time. From there, you just divide the number of threads in total by the number of threads available in the cluster, and you get some number of data nodes. But again, I'll stress one more time, you do have to observe empirically what's going to be the speed of the search and treat that as a constant. One more thing to do before we wrap up is to think about hot, warm, and frozen, and then also dedicated node types. If you plan on having a tiered architecture, you should size each of these tiers independently. Size your hot tier using the ratio that you want and the hardware that you want. Do the same for warm and do the same for frozen. And when you do that, and then you think about what are the dedicated types of nodes that I need, like I'll have dedicated master nodes, maybe dedicated machine learning nodes, or if I have a hybrid use case, dedicated coordinating nodes. I make these decisions, and what I get at the end is this overall methodology that I can follow for capacity planning for Elasticsearch. For each tier, we'll size hot, warm, and frozen. For each of those, we're going to make sure that we have enough data and that we have enough nodes just for the compute throughput, right? And that we're not either providing too many shards or too small of shards. We'll combine all of those sizes and make any decisions on dedicated nodes, and altogether that will give us a picture of what types of resources do we need, how many, and how big should they be. And that's it. That is effectively the overall how to size like an Elasticsearch solutions architect methodology. The last 2 things I'll kind of end with is that if you want to become more of an expert in sizing Elasticsearch or just operating Elasticsearch and doing all the great things that you can do with it, some of the content that we talked about here was pulled from a much broader set of course material that we have for our engineering 1 and 2 courses, which also can now culminate into an Elastic certified engineer certification that you can acquire. And I would recommend everybody to do that. It's a great experience and definitely showcases your expertise with Elastic. Now, if you are planning on going big and you want the help of an Elastic Solutions Architect or a consultant, we do offer consulting as well that can help you make the right decisions and even make empirical decisions. Sometimes it's not enough to make estimates based on assumptions, but you have to do some benchmarking tests. Our consultants could help you, for example, run a benchmarking test with our Rally software and also dig in deep with you on your strategy and your requirements. So our consultants can help you there as well. So thanks everybody today. And if there's any questions, be happy to answer them. There we go. Okay, yeah, a lot of questions here. Okay, fantastic. All right, let's see if there's anything here that has not yet been answered. Okay, here's one. So if NAS, network attached storage, is not recommended, then how does storage by GCP or AWS or Azure work, or are they not network attached storage? Yeah, I would say when deploying on a cloud service like GCP or AWS or Azure, you'll have some options for storage media that isn't network attached. And I would also be careful to say that I really am specifically talking about network attached storage as a protocol and not as, let's say, a SAN. Or, for example, on AWS, they have elastic block storage, and there's a lot of people that use that, and it works great for them, especially provisioned IOPS with SSD-backed EBS. That can definitely work. I know for our own hosted Elasticsearch service, which runs on GCP and AWS and other cloud providers in the future, what we will do is use instance types that actually have local storage on them. For example, on AWS, you have the i3 series, which are locally attached SSDs, or the D2 series, which are locally attached hard disk drives. And those are our preference because they just offer great performance and stability overall. So that's a good question. Okay, so there's a question here on HDFS and being able to, someone says, can we run on HDFS using HDFS, for example, as storage for Elasticsearch indices? So in Elasticsearch, all the storage is going to be done on a POSIX-like file system, is probably the best way that I can describe that. Meaning you can have different types of file systems on it. You can have different like SANs or things that maybe you mount differently. As long as you have a mountable file system that you can interact with, let's say if you're on Linux or Windows, like any other file system, then you should be able to use that. So that would exclude, for example, HDFS or S3, because those aren't quite the same. They don't have the same like file system level APIs. And you interact with that in different ways. So when it comes to HDFS or S3, we typically use these as repositories for snapshots, meaning you can take a snapshot of all of your data and put that on HDFS, put it on S3 as backup, and then you can restore that back into Elasticsearch if you need to. But you can't operate on that data, for example, doing a search on data that is stored in HDFS or S3. Okay, here's a question. If I have a limited number of data nodes available, can I ignore the memory to disk ratio and add the amount of disk needed to hold my data? What issues should I look out for? Okay, yeah, so thinking about, could I just have like let's say 20 terabytes of data on each of my data nodes? You could do that. And it's easier to do if you have a frozen index. That's actually one of the purposes of a frozen index, is to be able to densely store information on a single node. Some things to keep in mind is that the bigger your the bigger your disks are, right, or the amount of data that you have per node, the slower your searches are going to be. And at some point, there will be a point where it's just like untenable, and you could run into issues, let's say during recovery, when you have to recover so many shards or so many large shards. That can be a potential thing that you want to look out for. So in general, I think if you follow the best practices that we've observed, right? So these are ones that over time through our support and consulting and solutions architects, we've kind of come to the conclusion that, having, 64 gigabytes of RAM is a good thing to shoot for per node. Having certain ratios of storage for each of those amounts of RAM has been observed to give good performance. If you can follow those best practices, you'll be on a good path for having a good starting point with which to start your deployment. Yeah, okay. So are there different sizing recommendations for dedicated node types like master nodes, machine learning nodes, ingest nodes? I mentioned earlier, I think when you're sizing a master node, those can be small, and by small, have 4 to 8 gigabytes of RAM, maybe 16, and at least have 2 CPU cores for having better parallelism. They don't do too much. The thing to remember for them is that if you can keep them totally isolated from the data nodes and not on a data node, then you're going to guarantee that the work that they have to do isn't going to be interrupted by some long-running search, for example, or just other things that can happen with data nodes. For a machine learning node, some things that you might think about, and I won't get into too much detail because I think it deserves its own conversation. But in machine learning, what we do is we try to baseline a model for what is normal for your data, whatever parts of the data you want us to look at. And that could be very lightweight, potentially. If you're saying, I want to look at the average number of bytes coming in and out of my network over time, that could be a very lightweight machine learning job, as we call it. And it's not going to use too much memory or compute. But you could also say, let's split that job up and measure the average number of bytes coming in and out of my network for each user or IP address on my public-facing website. And now you've got a model for every individual person touching your website, which is going to use a lot of RAM, and it's going to use up probably a lot of compute as well for all that number crunching for each individual model. So it can definitely wildly vary in terms of resources needed. The ones that it will need at scale will be memory and compute, and it's a whole different sizing exercise, really. That's what it comes down to. And then dedicated ingest nodes, you probably will be wanting to allocate some more CPU because the whole point of them is to do data processing of data as it is ingested into the cluster. Oh, wow. I just realized I could scroll down, and we've actually got 5 pages of questions. Thanks to the other solutions architects who are on the call, able to help kind of answer those in the chat room. Okay, how is a coordinating node configured? A coordinating node is always there, really. Any node is a coordinating node, but you can make it a coordinating only node, meaning it's only going to serve the role of a coordinator if you just disable all the other roles. So by default, a node will be a master node, a data node, and an ingest node, I believe, is still the way that we do it. If you just say to disable those in the configuration file, then it will become a dedicated coordinating node. Okay, is there a rule of thumb when sizing data nodes for memory? So I have X amount of indices, how much RAM should I use? Okay, we do have some kind of go-to ratios for different types of use cases. 2 common ones that we see for logging and metrics in APM would be a ratio of 1 to 30 for a kind of general purpose logging use case, which balances the performance of your search request for logs and all the charts that you create with it, and being able to keep it reasonably cost effective. And then for a warm tier, we might see 1 to 100. And frozen, we can see people going up to 1 to 200, which is the maximum that we do on Elastic Cloud Enterprise, but you can still go further. We've done some benchmarking and have found no actual real limit yet, but we stopped at 1 to 1,000, and we found that you could still do searches just fine with having that much storage on a single node for a frozen index. If you have a search-based use case, you probably want a tighter RAM to disk ratio. So if you have e-commerce or just some other application search that you're powering, then having a ratio of 1 to 4, 1 to 8 or 16 are not unheard of. Again, the more RAM that you make available proportionate to the amount of storage that you have, it's just more data is going to be cacheable and allow you to have faster searches. So having a 1 to 4 ratio means that you have comparatively like a lot of RAM compared to the amount of storage that you have. Okay, a question on log stash sizing. Yeah, for the most part, in this whole webinar, we talked about how to size Elasticsearch. And sizing for Logstash is something that a lot of people still think about because a lot of people use Logstash. And if you are, especially if you're bringing in a whole bunch of data, you do have to think about at some point, you might need more than just one Logstash node, let's call it. And to do that, you might have multiple Logstash nodes, and maybe you load balance them so that when you ingest data, it goes to one of these Logstashes. And if you plan for that, you could just start adding Logstash nodes without having to change what you're doing at the client side, ingesting data. But how big should the Logstash nodes be? It's a different type of exercise, and similar to how I can't really predict how, let's say, how fast a search is going to be based on whatever query logic that you expect or the hardware. There's still no real way for me to guess like how many milliseconds a search is going to take for you. It's the same thing with Logstash. I don't know really how fast an individual process is going to take for a record coming in through Logstash because there's so many different things that you can do with it. But what I can say is that similar to search sizing, if you can measure a sample of whatever process you choose to implement, whatever pipeline, run the data through it and just see how many indexing events per second you're able to get using that, then you can just start there and start extrapolating out. Some resources to think about is that obviously Logstash is going to be compute intensive. It may require a fair bit of memory in addition to that. For example, there's things like translation tables that we will use for enriching data. And we have like, enrichment tables that you might use to just enrich your data. Those types of lookup tables might use up some memory. You might also have a fairly large queue. If you plan on queuing up a lot of messages in Logstash, that might be more resource that you want to plan for as well. In general, I think of Logstash as being primarily a compute-bound type of process. Okay, a couple questions on compression. So yes, compression does cost more in terms of compute. So if you use the best compression flag when you have your index settings, it will take a hit to your search and indexing throughput. And generally, I found that most people will just do it because the benefits outweigh the cost usually, right, in terms of your storage savings. Do you have to decompress it when you're searching? I don't know exactly for sure if a decompression happens during the search. I do know that the compression mostly applies to that source field, which isn't really searched. It's more just fetched and retrieved to the client. So that, of course, will have to be decompressed once you fetch that document and send it back to the client. So what is the typical spec of a data node? There is a link, and I might have to go find it, but you could probably Google it pretty quickly. On our Elastic Cloud documentation, there are a list of the different instance types that we use for the different hardware profiles that we support. So on our Elasticsearch service, you can have like a compute optimized hardware profile or an IO optimized hardware profile. And under the hood, they're using these instance types. For example, on AWS, our general purpose IO instances will use the i3 series instances and carve those up into containers. The warm tier, if you want denser storage that's more economical, will be on a D2 series instance. So the reason I bring up these examples is that you can follow what we do as a best practice for our hosted Elasticsearch service and use that as inspiration for what would be, absent of any like real benchmarking or empirical testing, like what would be a good general purpose node specification. And so I say, 64 gigabytes of RAM, 8 to 16 CPU cores for a data node, right? And that's comparable to what we do on our own hosted service. Okay, what would be a good technology to measure and display metrics or charts on ingest numbers and throughput? There's a couple things potentially. One is, I know that the licensed software that we offer has a monitoring section in Kibana that will give you some metrics on indexing throughput and search throughput and the latencies associated with them. So you can just go into Kibana, pull up those dashboards, and see what's the health overall, right? But you can also go in deeper, and one thing that you can use to get like fine-grained insights on specific searches on specific indices would be using Rally, which you may have heard about if you've tried looking through our documentation on ways to do this. Rally is our benchmarking software that we use internally and that we use with consulting and many people use. It's an open source tool with which you can do some out-of-the-box, like loading representative data, let's say of logs or other types of data, and then doing a battery of different types of searches and doing them very rapidly and just automating all of that. And it's going to measure the latency of all these different types of operations in the throughput and say, well, here's what we expect. On your hardware, on these types of data sets, we observe X amount of latency and throughput for these different types of queries. And you can customize that to use specific data and specific types of searches, which is one of the interesting things about Rally. So if you can get that and get realistic data on realistic hardware, then you can get some really good numbers that will be useful for you. Much more useful than even really the types of questions that we went through in the webinar, because they're actually based on facts and not best practices or kind of heuristics. Okay, there's a question here. Can we get the recommended ratios and all the other content in writing? Yeah, so this is a recorded webinar, and we'll make sure that this is going to be online, and you can go back and replay the recording and get that information that you need. We also are taking a lot of this content and adding in some other things like labs and exercises, and we offer this as a workshop. So if that's something that you'd be interested in doing and saying, hey, in our region, we're in Atlanta or New York City, we want to try to get together and just host a workshop on how do we do sizing and get more hands-on and do some real-world examples. That's something that our solutions architect team has done with great success, and is actually one of the reasons why we had this webinar, because it was so successful. So be on the lookout for those sizing workshops. And if you want to try to entice us to come to your region and host one, definitely reach out to us as well. Okay, does the 20 shards per gigabyte of heap count for primary shards or replicas as well? And the answer is yeah. So every shard is, really it's the same. Each shard, in fact, a replica shard can be promoted to a primary shard. So there's no real difference between the shards other than which one is assuming the role of a primary. So each shard has metadata associated with it, and it is something that may or may not actually be hit when it's searched. So they all are something that you should think about when you're doing sizing, and treated the same. So that 20 shards per gigabyte of heap, for example, or the ideal maximum size of 20 to 40 gigabytes per shard are applicable both to the primary shards and the replica shards. Is Elasticsearch suitable for the retail domain, like having transactions, product masters, inventory data? Yeah, all of the above. There's a lot of e-commerce websites using us in the retail domain for those types of data sources. What is the ideal way to get rid of older indices, right? Yeah, so we thought about, how do we plan for the capacity for the period of time that we want to keep the data, but at some point we're also going to want to retire that data, either deleting it or moving it to a warm or frozen tier or archiving it. There used to be a tool that still exists, it's called Curator, that would schedule the movement of data based on these retention policies. But now there's actually a native feature within Elasticsearch that allows you to do that. It's called Index Lifecycle Management. And the way that it works is you say, I want a policy where I have 7 days of data hot for this index. After 7 days, go to the warm tier for 90 days, and then delete it or put it on S3 or HDFS after that. And Elasticsearch will then handle that whole schedule of moving data where it needs to go. How to determine how many shards per index? Yeah, that's another interesting exercise to think about. If I have an index, how many shards should I have? One of the first things that I do just from a sizing perspective is think about how big do I expect the index to be? And if it is a big index and that's going to exceed, the ideal maximum size of a shard, then I would at least take that size and divide it by the ideal maximum. So if I'm a logging use case and I expect to bring in a terabyte of data every day, then I don't want to put it into an index with just one shard that is a terabyte large. I want to divide that by 20 or 40 and have that many primary shards. I might reduce that as it goes to a warm tier and have bigger shards, which you can do, but that's how I would start. And sometimes I'll also think about, maybe I have a whole bunch of applications and they're all writing to different indices, and each index maybe is a couple megabytes, every single day that these indices are created. I know that that's probably going to create a whole bunch of shards that probably don't need to be configured like that. I might collapse these indices together and maybe differentiate the different types of data by a field and allow me to reduce the number of shards by putting one index. Or instead of having a daily index, small amount of data, maybe I make that a weekly index or a yearly index, something that really allows me to cut the number of shards that I'm storing inside of my cluster. those are some ways that I think about how to plan for how big the shard should be and how many shards per index. Is it better to use a single large file system or to use multiple smaller disks? How does Elasticsearch stripe segments across multiple devices? So you can do both. I do think that you will get benefit if you use like a RAID 0 configuration, and you just put more disks on. If you have, let's say, a terabyte of disk on a node, and it's like that one disk, or if it was, 256 gigabyte storage devices, and those are all managed with RAID 0, you're probably going to get better performance with the RAID configuration. But both of them you can do. If I have a host with 120 gigabytes of RAM, can I run 4 containers with 30 gigabytes of JVM heap each? So let's see. So if I have a node with 30 gigabytes of heap, that probably means that the node itself has about 64 gigabytes of RAM, assuming I'm trying to aim for that, at least having like 50% of my data useful for the operating system cache. So I would say that if you have 120 gigabytes of RAM, you could probably run 2 containers, each with 30 gigabytes of heap each. You might also just take that 120 gigabytes of RAM, make it one node, and let it have 30 gigabytes of heap with more RAM available for caching. And that could be, potentially an option that you would consider. Is there a recommended maximum number of fields in the index, or is having an index with 2,000 fields okay? Actually, yeah, this is a good point, and it's similar to having a whole bunch of shards. There is a practical limit that you'll probably run into at some point if you have too many fields in your index mapping. If you Google the term mapping explosion, this is one of the, I guess, phrases that have been coined by people who have observed that as you start going up to like 10,000 fields in a mapping, things just start kind of grinding and not performing the way that you expect. So yeah, I would say I don't know exactly what that sweet spot would be for the ideal maximum number of index fields, but there is a limit to try to stay under. And I would put it this way, if you're in an order of magnitude for fields that is in the thousands, you probably have too many fields. And you want to probably start cutting that down to the hundreds if possible. And make sure that you have good control over how your mappings are constructed. For example, Elasticsearch has the ability to let you just dynamically create fields that are added to the mapping or the schema. The thing is, if you do that and you don't really have control over it, and you just allow anybody to create fields, the number of fields in the mapping keeps growing and growing. And at some point, you'll hit that practical limit of having too many fields in your mapping. So I would say in production, don't allow dynamic mapping, dynamic fields to be created. Understand what it's going to be and try to keep it, not in the thousands in terms of fields. Okay, when you go to a search, is it going to hit every node? Hang on, let me reread this. So when you do a search, is it going to hit every, I think, shard on every node that contain particular shards? I think I'm reading that right. Yeah. Okay, so search behavior. When you execute a search, actually, let's start with indexing. When you index a document, that document is going to go to some shard in the index. And the way that it goes to the shard by default is whatever the ID of that document is, it's going to be hashed. And there's this algorithm that decides, okay, you're going to go on shard 5 of 5 or 1 of 5. And then every time you index that document, it'll always go to that shard. At search time, you don't have that benefit. And because you'll be searching for some arbitrary term, right, that might be in any one of these documents. So it has to go and look at all the shards, whether it's a primary shard or a replica. But if you have 5 primary shards and 1 replica each, for example, then every search that you do is going to hit 5 of those shards. So the way that you can cut that down is by using that routing parameter, which you have to define when you index the data, and you have to define it when you do the search as well. Yeah, and what that allows you to do is basically say, for this type of document, it's always going to go into this particular shard. And so that when you do the search, you know that it's only going to hit 1 shard. It's a great thing to keep in mind when you're trying to scale for throughput, because when every shard is always searching for every single search, that can definitely slow things down at scale. That's called the routing parameter. Actually, a good question also would be like, what would be an ideal minimum size cluster? And still ensuring that you have all the benefits of high availability and data loss prevention. There's different, maybe potential different types of minimum size clusters that are all technically viable, but some might be better than others. For example, you could have a cluster that is 1 node and it does all the roles of master node, data node, coordinating node. It has it all. I run on my laptop a whole bunch of 1 node clusters just for testing purposes. Now in production, I'm not going to recommend that because you don't have high availability. And if you wanted to do like an upgrade, you would have to bring down your 1 and only node and you'll have downtime. So that brings you up to the next potential minimum size cluster, which would be 3 nodes, each with 3 master nodes and at least, say, 2 data nodes. Now, the reason why I don't typically recommend that anymore is because I think as a best practice, it's good to have those 3 dedicated masters that are small and off to the side. But even at like a small level, once you start doing things, let's say you take down a data node, well, if you have replication, those replicas are going to want to go somewhere. And if you don't have another data node available, they're not going to be able to get assigned to another node. So actually, the minimum size cluster that I typically recommend for people is having 3 small dedicated masters and 3 data nodes. And what that allows you to do, right, is you have your master nodes. They're not too big. They're off to the side, not too expensive. You have at least 2 data nodes, 1 for your primary, 1 for your replica shard, and then you have an extra data node. Now that data node is not going to be empty, probably, because you're probably going to have other indices that could also have data on there. But remember, whether a node goes down because of an outage or whether a node goes down because you want to do a rolling restart and upgrade configurations or things like that, then when you bring down that 1 node, you'll still have another node available for that other data to go. Now, especially if you've sized for really squeezing out the maximum amount of space on each node, you want to make sure that somewhere within across all the nodes that you have, there's enough free space available that that data gets to go somewhere. So that's my recommended minimum: 3 dedicated small masters and 3 data nodes. Okay, so here's one. Is there any advice for sizing with multiple indices, i.e. multi-tenant, on a single cluster? Okay, so actually multi-tenancy, when I think about that, there's many different ways that you could try to implement that. And there's actually a good blog post that we could try to find the link for that talks about this. And on the one hand, you could have a single cluster that has a single index for all the different tenants that you have, which may or may not be ideal for different reasons. It might be a lot of query logic you have to consider. There might be security concerns that you have to deal with. But nevertheless, it's an option. There's another where you could have a single cluster, each with an index for each customer, which again, pros and cons, some being that you have a lot more shards potentially, and your cluster might just need to be bigger to handle that. You also might have some customers that use the cluster in many different ways, and they demand like a search-heavy cluster, and others require like indexing-heavy, and some are just really chatty and just cause problems for other people. So a next step up might be having a cluster per tenant, or maybe having a dedicated cluster or dedicated index for really chatty customers. That's a way to do it as well. And as you start getting more and more complex, I think at some point it makes sense to think about what means of orchestration and deployment deployment automation are available for you to be able to make your life easier for that. We actually do have software that we maintain to do that. Our whole Elasticsearch service is powered by this thing called Elastic Cloud Enterprise, which is also something that you can download and use to manage multi-tenant environments. Whether that is having a way to manage, staging, dev, test, and prod clusters for one use case, or managing a whole bunch of different tenants and their individual needs. We also very recently, this week, came out with an operator for Kubernetes, which is in an alpha state. And we're definitely going to invest a lot in that as well. And having a way to take all that provisioning technology, like auto create a cluster, auto apply the upgrades and security configures and all those different things, and doing that on the Kubernetes platform. So those are different options available from a multi-tenant perspective. And from a sizing perspective, you just got to make sure that for any individual cluster that you have, you just got to size it for whatever the totality is going to be for that cluster, whether it's thinking about all the tenants that are going to be on it or that one single tenant. From a sizing perspective, you just got to think about it in the aggregate. All right, and I know there was a bunch of questions there I did not get to because I know there's about 7 pages here, but these are great questions, and I'll try to hop back on the chat and make sure that we can address some more of them. So following this, if you have more questions that you want to ask, a great place to do that is our discussion boards, which is discuss.elastic.co. And we break that up by the different software components that we offer. And our engineers are often on there to help answer questions for people. It's a great place for the community to just kind of share knowledge. You can also reach out to us on our website. And whether that is, for more guidance or maybe trying to figure out if we can have time with a solutions architect to see if you're ready to go production, maybe go enter a business relationship and what are the implications of that, reach out to us on our website. We can get in touch with you there as well. Thanks, everybody.